Hello, this is a quick video over some of those key topics you learned on week 1. One of the sections I would like to highlight is section 1.3 radicals. The definition that you should have been familiar with is the principal square root of a non-negative number is its non-negative square root. The symbol square root, a represents the principal square root of a. To name the negative square root of a, we can write it as negative square root of a. So notice how the negative is outside the square root. Typically, when working with square roots, we want to focus on a radicand that is positive. So here we have a list of examples. For example, A, we're asked what is the square root of 81? Well, the thought process that you should be thinking is, well, what number can I square so that my answer is 81? 9 works, so this means our answer is 9. We can also use square roots with fractions, like we see for part B. We're asked what's the square root of 16 divided by the square root of 81. Well, we can evaluate the numerator and the denominator separately. The square root of 16 is 4. The square root of 81 is 9. And some other situations, which you would have seen already in your other videos, is sometimes it's helpful if you write it under one radical. So you could also have changed it as 16 over 81. But for this case, it wouldn't have been helpful, since we can take the square root of each one separately. From radicals, another definition we should have learned is that when given some type of radical problem, if it can't be simplified directly, we can use factors and break down the radical to simplify further. A list of examples are here. So for part A, we're asked for the square root of 50. Well, there isn't a number directly that when I raise to the second power, we get 50. But is there a number that I can multiply to get 50 where one of them or a number of them are perfect squares? 25 and 2 work, right? 25 times 2 is 50. I can then split it. The square root of 25, the square root of 2. The square root of 25 is 5. And I can't simplify the square root of 2 any further. So our final answer would be 5 square root of 2. And we can use this with both square roots, cube roots, fourth roots, and so on. So for example B, we're asked for the cube root of 32, and I can't directly apply the cube root of 32, but there is a factor that would work. The cube root of 16, I'm sorry, not 16, 8 times 4. 8 times 4 is 32. If I consider each one separately, the cube root of 8 is 2. So we're left with 2 times the cube root of 4. And even though they're being multiplied, we don't need to write the multiplication. It's implied that they are being multiplied. And as for this cube root of 4, I can't simplify it any further, so it just stays as is. Part C, the fourth root of 48. I can't apply the fourth root directly, but there's factors that would work. 16 times 3. 16 times 3 is 48, and 16 is the number that I can apply the fourth root. So we can split it to be the fourth root of 16 times the fourth root of 3. The fourth root of 16 is 2. And so we're left with 2 times the fourth root of 3, or just 2 fourth root 3. If you feel like radicals are a bit challenging, I highly suggest that you become more familiar with numbers being raised to an exponent, because that's essentially what radicals are, working the other way around. So the note I was trying to leave is be more familiar with exponents. So you want to, if you'd like, we could list all the numbers raised to the second power, all the numbers raised to the third power, a bunch of numbers raised to the fourth. Not all of them, right? Maybe like the first 10, and then you'll be more familiar with what you're looking for. I'll make a list. We'll add a list of numbers raised to a power. Let's continue with another important section, section 1.5, factoring. Factoring is essentially working backwards from multiplying polynomials. And here we have an example. We're multiplying these two binomials, x plus 2 times x plus 5. We multiply, combine like terms, and this is our answer. Now factoring is when you try to go back. Sometimes we want a breakdown of what it would be before we multiply them. And to find that, we have to proceed by factoring. There are many methods of factoring. I believe there's about 5 to keep in mind. Here are 2 of the factoring methods for trinomials, meaning for 3 terms. The first example is when we're factoring a trinomial with a leading coefficient of 1, meaning there's no number in front of the x squared. A 1 is implied. A trick to consider when trying to factor is you want to list the factors of your C that add to give you your B. This A, B, and C come from your coefficients. So A is what x squared coefficient would be, B is the x coefficient, and C is your constant. So you want to look for numbers that multiply to give you C to add to give you B. In this case, our C is 21, and our B is positive 10. And I should have made that more clear for C. Our C is positive 21. All right. Well, what numbers work here? If a number doesn't come to mind right away, make a list of all the numbers that would multiply to give you 21. See if anything would match that description. In this case, 7 and 3 work, right? 7 times 3 is 21. 7 plus 3 is 10. So because we have an x squared, we're going to split that x into 2 factors, and our number that goes with it would be x plus 7 and x plus 3. We now have our answer, our 2 factors. So that when I try to multiply these 2 factors, I would result back into, if I try to multiply, I will result back on this side. Now that's probably the more easier situation of factoring. One that's more involved is called the AC method. We have our list of steps written down. This is a situation where our leading coefficient is not 1, but a number other than 1. So we have a trinomial 1, 2, 3 terms, and we want to factor. When you have the AC method, you first want to be able to factor any common factor. That's our step one. If not, you proceed by multiplying the A and the C. So A, B, C. You want to multiply the A and the C. 4 times 15 is 16. And you want to look for numbers that multiply to give you 60, but add to give you 16. It seems like 10 and 6 work. You want to replace it with your middle term. So you now have 4x squared plus 10x plus 6x plus 15. Notice you didn't actually change what you were given. You just rewrote it to force a fourth term. Since we have 4 terms, we can proceed to factor by grouping. Let's group our first 2 and our last 2. Looking at the first 2, I see that we can factor out our greatest common factor is a 2 and an x. Meaning a 2x is the biggest number we can divide the 4x squared by and the 10x. So what's left inside the parentheses now is a 2x plus 5. And we want to also factor the greatest common factor from the last 2 terms. For the last 2 terms, our greatest common factor is only a 3. So we're left with 2x plus 5. And if I'm moving a bit too quick, you can always think about the division separately. Divide each one. 2x, 2x, and then you'll get those numbers in those parentheses. All right, we can then proceed to factor out what's in the parentheses, which is a 2x plus 5, and left over we have 2x plus 3. Essentially, we have what's written outside the parentheses and what's written inside. All right, this is our answer. We have factored by grouping using the AC method. Moving on, sections 2.1 and 2.2, we talked about graphing. We were introduced to the rectangular coordinate plane, also called the Cartesian plane, also called XY axis. They all mean this figure here. And this how we'll proceed to graph most of our feature functions. We have our x-axis, which runs from left to right, our y-axis. Our middle point where they meet is called the origin. It's also the point 0, 0. And these 4 parts that are created are called quadrants. We start with the first one and then go counterclockwise. All right, you can go ahead and plot points. Your points are always given as x, y. So here we have the point, for example, right here, 6, -5. We find the 6 on the x-axis, match where it has the -5 on the y-axis, together where they meet is our point. One of the first features we learn to graph are a line. To graph a line, you have 3 main ways to go about it. You can use x and y intercepts, x-y intercept. Second, we can do a chart and pick some points. And third, for graphing a line, we can use the y equals mx plus b method. What's nice about the chart is that it will work for any type of function. What's nice about a third option, our slope-intercept form, that's the name of it, is that we can easily pick out the slope because it is always an m, and our y-intercept. Using intercepts separately, which is our first option I listed, is also helpful because it gives us key features of the graph. I'll proceed using the third option. So for a line, using that slope-intercept is really helpful. To graph using our slope-intercept form, you will first have to plot your y-intercept, followed by using the slope to plot more points. Alrighty, so for this case, our y-intercept is 3. Yes, it's always a number that doesn't have the x. So our y-intercept is 0, 3. So we have our point right here at 0, 3. It's always on the y-axis, hence for our y-intercept. We have a slope of -1/2. From our notes, we saw a slope is our rise over run. Rise means it goes up and down, run moves left to right. Since we have a -1, we're going to go down 1 point. A +2, we're going to go to the right 2. So from our y-intercept that we already plotted, which is +3, we're going to go down 1 and to the right 2, 1, 2. This is our next point. I can go ahead and erase those markers I drew. Connect our point to give us our line. And there we have it. You can use your slope more to plot more points. Keep going down 1, right 2. And that's how we can plot using our third option, which is our slope-intercept form. Another section I'd like to highlight is complex numbers. In a nutshell, it's telling us what we can do when the inside of our square root is negative, which we were previously told is a big no-no. Generally, the punchline is, if I have a negative, you just write an I, and that takes care of the negative. We write complex numbers as a combination of real and complex, so you can have that pairing together. You just write a plus or a minus depending on the sign of the complex number to write them together. With complex numbers, in that section you learn how to add, subtract, and divide complex along with multiply. But again, we're just working on the highlights. And the punchline is that when I'm given a negative radicand to take the square root, I work just as before. And for the negative part, we write I. So our answer for this would be 3i. The square root of 9 is 3. Because it's negative, we write 3i. The section that probably is going to have a bigger effect in the longer term is quadratic equation. So we were introduced to the quadratic formula, which is given as x is equal to -b plus or minus the square root of b squared minus 4ac all over 2a. And one important thing is you have to make sure it's set equal to 0. If it's not equal to 0, change it. So I have an example for you here. It's asking us to solve 5x squared plus 8x equals -3 using the quadratic formula. We first find the standard form so we can label a, b, and c coefficients. Meaning, let's go ahead and make sure it's set equal to 0. So we have 5x squared plus 8x equals -3. Let's move 3 by adding 3 to both sides. We have 5x squared plus 8x plus 3 equals 0. Now let's label our values, a, b, and c. Our a is always a number in front of the x squared, our b is always a number in front of the x, and our c is our number without a letter. So a is equal to 5, b is equal to 8, and c is equal to 3. Now let's go ahead and substitute those a, b, and c's into our formula. So that we have x is equal to, we have negative, our b is 8, plus or minus the square root of b squared, my b is 8 squared, minus 4 times a and c. Divided by 2 times a is 5. So we have negative times a is negative 8, plus or minus 8 squared is 64. Let's establish our sign. Negative times a positive is negative, and negative times a positive is negative, so it's going to stay negative. 4 times 5 is 20. 20 times 3 is 60. All of that will be divided by 2 times 5, which is 10. So I have x is equal to negative 8 plus or minus the square root of 64 minus 60 is 4 divided by 10. And we clean it up each step along the way. So we have negative 8 plus or minus the square root of 4 is now 2 divided by 10. So because this is a quadratic, meaning my highest exponent is a 2, it means that we have two answers for x. X equals a number and x equals a different number. It can be the same number, that's possible. So this is actually giving us two options because of the plus or minus. So x is equal to negative 8 plus 2 over 10, and x is equal to negative 8 minus 2 over 10. Clean each one up. So negative 8 plus 2 is negative 6 over 10. We get negative 3 over 5. Negative 8 minus 2 gives us negative 10. Divided by 10, we get negative 1. So x is equal to negative 3 over 5 and negative 1. Those are our two values for x. Alrighty, this was just a really quick review of some important features from week 1. And they're all, of course, everything you learn in the week is important, but I just wanted to showcase some pieces of it. Again, I didn't go through everything as descriptive as it's introduced in the section, but it's just to highlight some features of week 1. Thank you.